Okay.
All right, here we go again. And thanks everybody for the opportunity to talk. Super quick outline here. We'll just talk a little bit about what the river forecast centers are and then modeling in the basin. And then if we have time, we'll talk a little bit about model errors and plans for improvement. So the River Forecast Center, here's the chain of command. We're under the Department of Commerce, and under the Department of Commerce, there's NOAA, or the National Oceanic and Atmospheric Administration. Under that's the National Weather Service, and then under the Weather Service is the River Forecast Center. Here's a quick map of the lower 48 in Alaska and Pacific, and you can kind of see how we divvied up the United States into different river forecast centers. So theoretically, everywhere is covered by our River Forecast Center in the United States here. So we're the Colorado Basin River Forecast Center, and it's kind of divided up into largely the upper Colorado Basin, the lower Colorado Basin, and then we get a big chunk of the eastern Great Basin as well. So a quick background on the Colorado River Basin. It's a desert basin that gets snow in the mountains in the north part of the basin, essentially. So it provides water and electricity to 40 million people. It provides those things to a lot of big cities, and I underlined a few that are not in the basin. So we pipe water that we collect in the basin out of the basin to Denver and Salt Lake and LA and Albuquerque, as well as everything within the basin we need to support. It supports 5.5 million acres of croplands and pastures, provides recreational opportunities for rafting, fishing, boating, hiking, et cetera, and serves as habitat for fish and wildlife species, including endangered native fish. Provides those things to 15 Native American tribes, 7 national wildlife refuges, 4 national recreation areas, 5 national parks, and supports almost $700 billion worth of the economy. And that's just direct effects of the economy. There's almost that much in indirect effects. Supports 2 countries, the United States and Mexico. And interestingly enough, we have about 16 million acre feet of average annual inflow into the basin from precipitation and snow in the mountains, and 16.5 million acres are spoken for. So we have more people that want water every year than we have water to divvy out. And then the other interesting thing is we have about 60 million acre feet worth of storage in reservoirs and only 16 million acre feet coming in every year. So people built reservoirs thinking that we had a little bit more water than we do. This is average annual inflow. So sometimes we have really big years and sometimes we have 2 years in a row that are really dry years like we have right now. So it's important to do river forecasting. A side note, the Weather Service is really good at acronyms. I'm going to try my best to not use any acronyms, but CBRFC is Colorado Basin River Forecast Center. So you will see that one, but by all means, let me know when I start saying things that you don't understand in terms of acronyms. So the River Forecast Center provides impact-based decision support. That's kind of a large part of the job, is helping water managers figure out how to best manage their water. Some of the biggest stakeholders that we have is the Bureau of Reclamation, smaller water conservation districts, even smaller irrigation districts, and then down to the farmers, dam tenders, boaters, et cetera, anybody that wants to know how much water there is in the streams. And a really important thing is that we exist to provide an unbiased forecast, right? There are large implications of the numbers that we put out in terms of telling people how much water there's going to be in the river. So it's important for us to not have a dog in the fight. We don't have any interests in whether we say there's a lot of water or a little bit of water, but that's an important feature of the river forecast centers. So quickly, our main products are the 10-day forecast. So every morning we come into the office, we clean up the temperature and precipitation data, and we run the model forward. That model is used to predict stream flow at about 700 or 478 locations. So every blue dot in this center map, we put out a 10 to 15 day forecast, which is essentially just a hydrograph of what we think the river is going to do. And then at 174 location, we put out water supply forecasts, and we put out official forecasts either monthly, twice monthly, and we provide model guidance daily. But anyways, all these little triangles that are warm colors, which means really dry, are the water supply forecast points. And we'll talk lots more about that in the upcoming slides. Other products we put out are kind of peak flow forecasts, recreational reports, and then model anything that our model has, we make that available to the public. So if you want to see how much snow our model thinks is in the mountains, you can look at that, or how much water is in the soil. And then I'm just going to kind of step through modeling in those products here. So the forecast system we use is a model. So we model the hydrology of the basin. We use a model called Snow 17 to model the snow. It's a temperature index snow model. So essentially, the only two inputs that it needs are precipitation and air temperature. The Sacramento soil moisture accounting model is a lump parameter model. It's the hydrologic model, so everything at the surface and underneath that makes stream flow. It's also a lump parameter model. The model uses hydrologic response units, which is just a big chunk of the earth that you think behaves similarly hydrologically. So we divide those up by elevation band, essentially, to make things easier at this point. And then we just use a simple unit hydrograph model to take water from those hydrologic response units and turn it into stream flow. So we'll talk about the 10-day forecast and how we make that. Essentially, here's that same model that I just described to you. So we'll put in the air temperature and precipitation for the last 10 days, and then we'll use a forecast for the next 10 to 15 days air temperature and precipitation, and run that through the model and get a hydrograph. So what you're looking at down here is one of our most popular products. It's just the hydrograph. The dark blue is measured stream flow, and then the green part of the hydrograph is our 3-day forecast. That's the forecast that we think we have a pretty good handle on. And then from 3 to 10 days is this kind of pink dotted line, and that just shows that we're a little bit less certain about that, but that's our best forecast of what the precip's going to do. A couple of other fun things about this chart is it kind of shows you what the normals are. So the line between the dark blue and red is normal stream flow for this time of year, and then the light blue would be pretty high flow, and the light red would be pretty low flow. So it's a low year. You can see we're below kind of the 10 percentile of where stream flow usually is this time of year. I'm not going to talk specifically about droughts or low water years in this talk, but you'll be able to see in a lot of the figures that I show that we're in a bad way when it comes to water supply this year. So at the end of the model run, we essentially have soil and snow conditions for today. So tomorrow we'll start with those soil snow conditions and run the model forward, and the loop continues. This down here is just a map of the Weber at Oakley, one of my favorite headwater basins, and it just shows you how we divide up a basin into hydrologic response units, or elevation zones. So it's a map view. You can see the light blue would be the lower elevation zone, medium blue the middle zone, and the dark blue would be the upper elevation zones. So we only have to run the model once for each elevation zone to get stream flow at that place, which makes it a very efficient modeling system, which allows us to, model the hydrology of the whole Colorado Basin every morning and get forecasts out to everybody. So yeah, like I said, make sure you're interrupting me with questions along the way as we go. Am I talking too fast, or everybody in good shape still?
You're doing wonderful.
All right, we'll assume.
You're doing wonderfully.
I hear a question. Great. All right, so on to the water supply forecast. It's kind of our other really big product. It's a volume forecast. We provide this forecast in thousands of acre feet or kiloacre feet. It's my favorite unit of measurement, a mixing of imperial and metric systems, or percent of normal. A lot of people just want to know kind of if we're much wetter or much drier than normal. The volume is an April through July volume. So essentially, water managers out here want to know how much water they're going to get out of the spring snowmelt runoff. And like I said earlier, we put out an official forecast monthly. We provide daily guidance from the model. And these are high impact forecasts. Essentially, there are water managers like the Bureau of Reclamation that have to use our forecast to make high impact decisions. So it puts those guys into kind of drought categories. So if we say there's not going to be much water, they start telling people you can't have as much water as you think you're going to get. So this is why it's really important that the Bureau of Reclamation doesn't do their own water supply forecasts, because they know where the thresholds are for those forecasts. So they know it's a lot more work for them if we say it's 30 million acre feet instead of 29 million acre feet. So that's where we come in and we provide an unbiased best forecast that we possibly can for how much water they're going to get in these big reservoirs like Powell. We'll talk a lot about this graph coming up in the next couple of slides as well, but that's kind of what we call an evolution plot, and that's how we present our water supply forecasts. So this is how we run the model to get the water supply forecast. It's a little bit more complicated than the 10-day forecast. Here's the model that we showed on the previous slide, and here's those model states, as we call them, the snow and soil conditions for today. So at the end of today's model run, what's today, April 21st, we know we have a modeled soil and snow conditions. So we start with those snow conditions on April 21st, and then we look at the last 35 years of air temperature and precipitation data. So we're starting with the model states for today, and then we take air temperature and precipitation data from April 21st to August 1st from 1981, and we run that through the model and we get a hydrograph. Then we take air temperature and precipitation from 1982 and we run it through the model from April 21st to the end of July, and we get another hydrograph. And then we do it for 1983, and then we do it for all of these, usually 30, but right now 35 years, and then we get 35 kind of possible hydrographs that describe essentially the spread and possibilities that we're going to get from this year's snowpack and soil moisture conditions. So what that does is it gives us a spread, like I just said, of different hydrographs that you could get based on unknown future weather. All right, so we have those 35 hydrographs, and essentially what we do is we deliver this information probabilistically. So we'll take the hydrograph from 1981 and we'll get a volume from it. So we have one volume. And then for 1982, we'll take the 1982 hydrograph and we'll get that volume. And then we do that for every year for 35 years, and we get 35 possible volumes that you can get from this year based on historical weather conditions, essentially. And we just present that essentially in a modified box plot, you can think of it, except for instead of using the inner quartile range, we use 30 and 70 percentiles. And we present it with exceedance values. So this lower volume, we would say, well, you have a 90% chance of getting that volume or above. And then a little bit more volume, that 70th percentile, we say, well, you have a 70% chance of at least getting that much water and above. And then the median value of those 35 volumes is the most probable value. So that's kind of our most probable forecast. And then, well, you only have a 30% chance of getting a lot and only a 10% chance of exceeding this very high volume. So that's essentially what we do. And then we in that evolution plot that I'll show you, we just present that in this kind of hot pink line with pink dots on it. And then since we run this model every day, you know, these pink lines are the official forecasts, but we run the model, we say, well, we'll just provide what the model says every day. And we present that in kind of this vertical blue line that goes from the 10 to the 90 with a dark blue dot at the median value. And that just kind of marches across to the right with time. So every day that line will grow just a little bit longer to the right. So to make more sense of that, this is what that evolution plot looks like. On the left, you have volume in thousands of acre feet. On the y-axis, and on the x-axis, you have time. So this was our official forecast for January 1st. And then February 1st, you got that official forecast. And then March 1st. And then in the background, you kind of see the model guidance day to day. So if it snows a lot and you want to see what that storm did to your forecast, well, you just look at the blue line and it'll either jump up or stay the same depending on what impact that has on our models. So the evolution plot has a lot of other information. If you pull this up from our website and you hover your mouse over it, the legend will populate with the different numbers for you. And in the title, it gives you the most probable forecasts and percent of average or median. The other things you can kind of click on and off are, it'll give you the maximum and the minimum volume, April through July volumes from the historic record, and then central tendencies and those green lines in the middle there. Other things that it'll show is kind of normal accumulation. So this will start in April and end at the end of July. So that's normally how much water would accumulate over time. And then once you get into that period, this kind of orange area plot will start filling in so you can see what observations look like and how it's actually accumulating. So all that to say, that's one of the more important products that we put out in the Colorado River Basin. And it can get complicated in a hurry, but if you break it down piece by piece, there's a lot of information you can get out of it.
Patrick, I have one question for you.
Sure, thanks.
So if you look at 35 years of data, didn't the land use also change over time, and is that considered?
Yeah, we are doing a few things to consider more fire-related land use change, but I guess the real answer to your question is no. The variability from precipitation and in temperature over those 35 years is kind of handled in that spread. And every time we get another 10 years of data, we'll stop using the oldest 10 years of data. So we're only using a 30-year moving window to account for that land use change. And we recalibrate our model every time we get 10 more years of data as well to kind of deal with that non-stationarity. So I guess the answer is yes and no. If the land use change within the past 30 years affects that hydrograph, you'll see that effect and it won't be accounted for in the basin in the forecasts. But if it's kind of a longer, slower land use change process, then it will be accounted for in the forecast.
Thank you, Patrick.
Sure, thanks. So that's kind of the first part of the talk. We'll move on to kind of errors and what we're doing about it from here on out. But looks like I've got about 10 more minutes left before a more formal question and answer session. So if anybody has specific questions for that first half of the talk, I'd be happy to answer it, or I'll just kind of start moving on. Okay, well, here we go. So those are forecasts, and we use a model to do it. So there are errors, right? We do not know how much water is going to come through the stream, and we do our best to be really honest and clear about how well we do and how we do in different places and in different parts of the year. So on our website, you can go to water supply verification, pick any year, see how we did, and then we have kind of on average, this is how we do. In general, we do really well in snow-dominated headwater basins with few diversions and reservoirs, and we do worse in low-elevation, rain-dominated basin with unknown diversions. So we try to be as forthright as we can and say, you know, we do really bad at this place, or we do really good at this place. But as you know, the river forecast centers are essentially always trying to make our forecasts better. So what we did is we just did a little study to figure out, you know, where does that error come from in our forecasts, and what can we possibly do to make better forecasts. So I'll just describe this study quickly. Essentially, if you imagine this kind of tan box as a total forecast error, so on April 1st, we say, okay, you're going to have this much water between April and the end of July. Well, there's some error in that, and we know what that error is because we have 35 years of reforecast data. So we can just take the mean error that we have from our model run for the past 35 years. So every April, we'll see what our forecast would have been and then compare that to the observed volume during that time. Well, that is divided into errors due to unknown future weather. So it's April 1st. We have no idea how much precipitation we're going to get from now to the end of July. And model errors. So there's lots of different errors in our model, right? The model errors can be from our model states are wrong. So we have the wrong snowpack in the model, the wrong soil moisture values in the model. We could have not calibrated the model well. So there could be errors in model parameters or model structure, which essentially means that our model isn't sophisticated enough to represent the important things that are happening hydrologically. So the model errors are a big group of errors, and there's lots of different things in there. The unknown future weather errors are you know, more simple to understand. We just don't know what the weather's going to be. But we can quantify the model errors because we have 35 years of calibration data. So we know the last 35 years of weather already, and we know how much volume our model said should have come out of the stream, and we know what the observed are. So we can quantify those modeled errors. And then we can just get the unknown future weather by differencing, right? We have the total error in an April 1st forecast. We know what the model error is, and then we can just back out the future weather error by residual. So we did this at a couple of our more well-behaved basins in the upper Colorado River Basin, and we found essentially that half of the error in our forecast is due to unknown future weather, and the other half is due to model errors. So this is useful in a couple of different ways, and the first way is just kind of, it's a framework to see where we should put our efforts in improving our forecasts, right? We have a 50-50 split. So if we want to improve errors due to unknown future weather, we can do things like evaluate new forecasts for seasonal to subseasonal weather. This is kind of a big research topic. There's lots of universities out there trying to make better forecasts, weather forecasts, way out into the future. And then we can look at global climate indices like El Nino or La Nina to do things like try to weight those historical traces with similar years due to those indexes. Model error is kind of, it's wide open. There's a ton of things we can do to try to improve those errors. So here's a big list of things that we're trying to do, and we're looking at I'll look real quickly at some external snow products that we're starting to look at to see if we can improve our forecasts by incorporating somebody else's snow product into our model. And we'll look quickly at kind of moving to a more physically based snow model instead of the temperature index model. So yeah, I've got about 5 minutes left. I'll just start marching through this and quit when I get to the end of it, and we can move on from there. So really exciting. We have a grant funded through NASA, NASA's Applied Sciences. It has a big long title and a number. But essentially, the really important things about this project are there's a strong research to operations component to it. So there's money in the grant for the researchers to come into our office, set up the model, educate us on how to use it, and evaluate whether it improves it or not. So this is a big push in a lot of funding institutions that you actually put these research to operation parts into your proposal. So it's with the University of Utah, the Northwest Watershed Research Center in Boise, where I worked for a while, and the Colorado Basin River Forecast Center. And another kind of side note is I know these people. They're friends and colleagues that we've developed relationships with through meetings and work groups and stuff. So that's kind of another, I'd say, important thing, that the network that you develop when you're in school is really important when it comes to your job and forming these kind of research partnerships. Physically based snow modeling, also close to my heart. We're using a weather model that essentially we're already getting in the National Weather Service. So the data that we use to run the models is already there. So this kind of gets over a hurdle that a lot of people get when trying to run these more complicated models. And it has some fun remote sensing components. So it uses both NASA and Weather Service satellites that are out there and kind of new remote sensing products. So
can I
one of the most, yeah, please do.
So in the modeling, where are you getting climate data, and how does the impact of climate change come into all of this?
Yeah, so
it's are you looking at?
The forecast. So the short-term data that we're using to run it to present, and essentially really short-term, like 12 hours forward, comes from the rapid refresh model, which is kind of a fun numerical weather model that assimilates data from a bunch of different ground-based stations and all the weather radars. So essentially, it runs every half hour or hour out 12 hours, and you can see
so these are really
convective thunderstorms and things like that.
Short-term forecasts, okay.
And that's in our model. But then so this would be our operational model. So everything that you've just seen, like using historical data and stuff like that. The office is moving towards a new framework where we use, instead of using historical data, it will use a combination of numerical weather models that are run actually pretty far, up to 30 days out into the future. And then from there, we have a lot of different options of forcing data that we can use it's an ensemble approach. So you can use things like historical data to try to capture the extremes, or you could use kind of climate indice weighted numerical weather models going forward.
Yeah,
but that's definitely a research direction.
I know in Pennsylvania it looks like we're getting a lot more extreme precipitation events as we continue with climate change. So I was wondering are you seeing those kind of things captured in your modeling, or is it not getting that stuff right?
The extreme events that we are not capturing very well are the thunderstorms and rain on snow events and things like that. Okay. The real day-to-day hydrographs from convective storms. And that's largely a function of the lump parameter model that we have isn't sophisticated enough to capture that high resolution input. The weather models and the convective schemes in the weather models are actually getting pretty good, but we're kind of lagging behind in the model. The seasonal volume, we're not seeing extremes in the term of that aren't captured in the historical data. So if we have a really extreme year, well, it's usually still within the 10%, the bottom 10%, or the top 10%, and the end users can look at that spread of probabilities and pick out their comfort threshold, essentially.
Right. So you're almost getting the averages better than the variability, it sounds like.
The way that our forecast system is set up, that we always, that most probable volume is the median of the historical weather traces. And if it's a very low year, like if we have really low snow, it's going to be low because we're using the model states from that day. And we're running it forward as if the most probable future weather was normal. Which we're seeing is often not the case in our forecasts, like this year, drop month after month after month.
Yeah. Okay. Cool. Thank you.
Sure. And then those climate indices, we just got a really great meteorologist on our team, and he's looking at weighting those those historic data based on what kind of, if we're in El Nino or La Nina, he'll weight historic La Nina or La Nina years heavier than the other years.
Right. Okay.
Yeah. Great. So, we're at 10:45 right now. I could just stop and take some questions if you guys want, or I could, go through some of the remote sensing stuff. It's totally up to you guys. I'd be happy to just have question and answer or discussions.
Any questions from students in the group? And if not, you can give us a couple minutes of remote sensing, Patrick.
Sure. Okay. And I'm assuming that as questions pop up, people will just interrupt me at this point. Okay, and then just a couple of pretty pictures saying that, there's all this satellite remote sensing data out there that do a really good job of fine resolution, both in space and time, of cloud cover. And nobody is really using this to drive physically based models. So this is kind of the low hanging fruit of this project with the university and Agricultural Research Service in Boise. So we're hoping to incorporate some of this data to better constrain the energy balance, essentially. Okay, and then, I'll just go through a couple of these external snow products that we're looking at. Some of them are common, and I'm sure you've heard of them, and some of them are less common, so maybe I'll introduce you to them. We use MODIS imagery, so from Terra and Aqua, but essentially they keep coming out with better algorithms. Their latest algorithm attempts to estimate the snow grain size, or at least the optical grain size from the satellite, which has a huge implication on the snow albedo, essentially how much incoming solar radiation is reflected back out of the snowpack. So we're trying to keep up with them and incorporate those into our model. So every day we see how much snow is on the ground in our basins, and we also get this mod DRFS product, which is dust radiative forcing of snow. It essentially tells you how much more energy is coming into the snowpack due to impurities in the snow. Just kind of really fun that people are taking pictures from space, essentially, and coming up with usable products like these that potentially we can incorporate into our forecasting system. So here's just a quick, this is kind of the poster child picture. A lot of the results aren't this good, but if this picture with the red hydrograph here shows that we're missing this big melt event peak in April, and then this other one saying, well, if we adjust our temperatures that go into the model based on the radiative forcing product that we just showed you, a lot more energy goes into the snowpack, a lot more melts, and we do a much better job of capturing that hydrograph. So that's kind of how we've already incorporated some remote sensing data into our forecast system. There's this product called Swan, snow water from artificial neural networks that a guy at Arizona State, also named Patrick Broxton, put together. So this is kind of the machine learning and incorporation of ground-based data to produce a snowpack comes in. So essentially, we can take anybody's snow product that's putting a snow product together. We can quickly calculate a basin average snow water equivalent. We can either bias correct it to our modeled SWE or just use it raw from the provider. And we can stick that into our model and see how much it changes the hydrograph. And we can do that for the past 35 years and see if it helps our forecasts. So this is more of kind of a test bed slide. We came up with a bunch of messy Python code and a framework that we can take other people's data, kind of stick it into our model and see if it helps the forecast. And this is kind of just due diligence. If people are going to go through the effort of making a snow product like this, we're going to take it and see if it's going to make our product better for people. A long story short is it didn't really help our forecasts, but it's similar enough to our forecasts, or it's similar enough to our modeled snow that we can use it to tell if we're way off. So if for some reason we were getting bad measurements from a snow tell station and our model snow was really high in a section, we can look at the Swan data and say, maybe we better take a closer look at that. They're starting to diverge pretty far. There's also this Airborne Snow Observatory. It used to be a NASA thing, and now it's a private enterprise. Essentially, they'll fly a basin with LiDAR without snow, and then fly it with snow. And you just subtract the two surfaces, and you get a volume of snow within a basin. It's fantastic remote sensing data. They'll estimate a snow density, and it'll give you kind of how much snow is in that basin. Estimated, of course, not really measured. They're doing a good job of measuring the depth. The problem with this is it only covers like one of our basin, and we have hundreds of basins, and it's only a snapshot in time. So it's really good, high quality data, but it's just not useful at this point for us because we only have 2 or 3 years of data, and we can't really evaluate it. So those are kind of the couple of products I wanted to be sure to get through with you guys, just to give the students a feel for what kind of data is out there, what we do, and how we use it. And I'll stop there for hopes that there are some questions out there.
All right. Well, first of all, before people start to depart for classes and things, we'll give you a round of applause. I'm proud of you to the moon and back, Patrick. You're like a mid-career scientist, and I think that forecasting for the Colorado River is creme de la creme hydrology in the United States, really critical. So, you know, as a mid-career guy, looking back on times here from McKees Rocks and through Slippery Rock on to the American West, if you did it again, what might you do differently, and what advice would you offer to our students in attendance today?
Yeah, I mean, it's a great place to be, and I've had a lot of help along the way. You know, the networks that you guys build by going to professional meetings and talks like this, and the networking really does matter. There's a lot of cool cats out there in earth sciences. They're my favorite people. And it's easy to build networks in geosciences, I think, because people are generally nice and wanna hang out with you. So the advice would be, don't be afraid to move somewhere and take a cool job. Go to meetings if you can, meet people, present. Elbow rub with people, get in conversations, tell them when you disagree with them, tell them when you do agree with them. And yeah, I mean, I've had it lucky. So hopefully that's good advice.
It's good advice. Believe me, it's good advice, but it's just wonderful to hear it from an alum, and that it lies in perfect agreement with what the faculty would tell our students to do, to engage and become active, and to do it sooner rather than later.
Yes, yeah, indeed.
So let me ask you to step back then, if you be so kind, off of the record, not speaking from the voice of your office. But I know that your job is to tell people unbiased how much water there is this year. Generally, we're in the midst of a mega drought. We have very dry conditions. We have accelerating and lengthening fire seasons in the American West. And part of the beauty of science is when we can give people valuable information that can affect decision making. Do you have any comments or insights about the issues that you see as both a resident and as a scientist?
Yeah, it's getting dry out here, and it's just such a complicated system, at least in the West, with the law of the river, and there's so much litigation and so much allocation and so many water rights issues that it's really hard to get a holistic view of how things work in even one basin like the Colorado River Basin. So it's painful to see that there's an over allocation of water, but it's also kind of heartening. I'm happy to see that people are starting to recognize this, and people recognize that we're in a big drought and climate change is a thing, and we're going to have less water. And there's a lot of people sitting down at the table, not the usual suspect, not just the hippies that believe in climate change, but farmers, ranchers, religious leaders, people that would never sit down at a table before are starting to sit down at the table and talk about what they're going to do with less water. And people are stepping up and saying, we can get by with less, we can conserve. So it's kind of, good news born out of bad news on that level. And I feel like that was a really rambly, not answer to your real question.
I
but
loved your answer.
It gave me the opportunity to ramble on a little bit.
I liked your ramble. I loved your answer. I think that coming to the table and realizing that we have issues and we have to talk about them, we have to be real, we have to cooperate. My goodness, I think that in there, that is the silver lining, because the great challenge that the professors in the gallery face is how to convey the magnitude and the power of the challenges we face tell the truth about that, yet inspire our students to be enthusiastic and optimistic for the future. And that optimism has to be born of cooperation and human capital. It has to be. We can't just make more water, so we've got to cooperate and use the water better than ever before.
Yeah, and there's a lot of social skills in there, right? You have to listen to the people that you're trying to convince and see what angle they're coming from. So there's lots of nerds with bad social skills. So if you can if you can learn how to listen to people and communicate well, that gives you a step up in life. And you know, there's nothing like going to these meetings and rubbing elbows to brush up on that kind of thing.
All right, Patrick, it was really, really sweet of you to come and spend time with us, and I thank you so much for it. I look forward to continuing and having discussions with you in the future and rubbing elbows with you at meetings and down the road.
Hopefully soon, yep.
Thank you very
well,
much.
I had a blast. Thanks, everybody, for listening. I appreciate it, and feel free to contact me with any questions or whatever.